sé si ahora el siguiente speaker que es nariz sí, ¿no? No tengo aquí una charla. Ya. Estas son las capitales que requieren después. Pues no se puede hacer sitio.
Sí. Tendrías que haberme lo mandado un poquito antes.
Perdón, es que no sabía cuándo.
Pues
Antes.
y yo, más que nada porque este ordenador no lo controlo muy las teclas. Pero ahora lo está viendo todo el mundo. Aquí está. Vale. Vamos a bajar la escritorio. No, Dani ya no la da, he cambiado. Sí. Vamos a terminar. ¿Esa? Y tiene celeste ya la. Este es el puntero, que está bien. Esto para así que si te vas a mover por aquí o aquí, pues. No, donde tú quieras. Tienes que llevarlo muy claro.
Vale. Sí, pues seguramente será algo así. Pasa que si lo hago en... So we're good to go? Okay, so welcome to the second part of the morning session. Okay, so our next speaker is Francisco Javier Marin Rodriguez, and he's going to be talking about scalar embedding of temporal network trajectories. So thank you.
Thank you very much, Samuel. I hope you can hear me back there. Well, I'm going to present my master thesis, but expanded by, well, my both tutors, Luis Arola and Lucas Lacasa, also Naoki Masuda. You can find the work online. It's completely free. Of course, please contact me if you have any doubts, right? So I'm going to start from scratch. What is a temporal network? We will consider a temporal network as a sequence of time-ordered snapshots, as a sequence of photos. Each photo is just, we can say that as a static complex network, as dots and lines between the dots. Dots are called nodes, and lines are just links, as you may know. I know that, but each one of those snapshots has a nodes, and it can be completely described with an adjacency matrix of n times m, right? So you can think of a temporal network as a sequence of those snapshots ordered in time. This is a way of modeling complex systems. So why do we use them? I'm going to be I'm going to stress this a lot, but well, we use temporal networks because dynamics and structure in the network share temporal scale. Being pragmatic, that means that not all links are active all the time. Moreover, those links are not generated randomly. They have a structure behind its generation. There is a correlation, and this can be observed in reality since in temporal networks, the intervent time distribution is bursty. What is the meaning of this? There are many events in which the intervent time is very short, and events in which the intervent time is long. And well, this is, of course, contrasting with, for example, the random disintegration of a particle, which is non-bursty. It is a random process, and well, please think about this lecture or maybe in school, because well, in a given classroom, uh, when the lecturer, when the speaker, when the teacher is giving the lecture, well, maybe all students are paying attention to the teacher. Well, they are hopefully quiet, and well, that means that there is somehow a structure given by maybe social pressure. We can say that, right? And the thing is that when break happens, when just like the coffee break, we have just taken that. Well, interactions explode. They happen to. There are classrooms that merge. There are even grades merge. Kids from different ages merge during the break. So that means that there is a varsity structure there, because also when kids leave the school, they do not interact each other until the next day, right? So that's why I want to stress this idea, and I want to tell you that that's why we use temporal networks, because not all the links are active all the time, because there is an structure behind those generation. No, that there is a dynamics. You know, we say that word in physics. And our hypothesis for this work, because I love the scientific method, and the scientific method says that we have to state a hypothesis that we can refute, and all of this that you already know, is that we can develop a method that produces low-dimensional time series representations from a given temporal network, while preserving, of course, the dynamics, the nature of the temporal network itself. How can we do that? Well, we will look to preserve the relative positions by each snapshot while doing the embedding, while obtaining the low-dimensional time series. How do we do that? Well, we take a temporal network, a given temporal network. Each snapshot has an GCC matrix, and we build a distance matrix out of all of those GCC matrices. Okay, with in this case we'll just use somehow an Euclidean distance between snapshots. This is somehow tricky. You can ask me later or somehow, because what is a distance between snapshots? Okay, this is a very interesting question. But the thing is that we just take this simple distance, okay, between snapshots, between graphs, okay, and that distance matrix serves as an input of the PCA or a multidimensional scaling as a reduction method, okay. So the output of the PCA are a number of principal components you choose. Well, we just choose one. We truncate a lot the PCA. We just take one principal component. And that first principal component that explains most of the variance is our low dimensional network trajectory. And I want to stress, and this is very important, each point of the low dimensional trajectory that is simply an scalar will try to be a faithful representation of a temporal network. You may say, oh, I mean, you have somehow turned an GCC matrix, an object that lives in an m times n space, into just one real number, into an scalar. Well, we will look at this with more detail now, because this is just the scheme of what we are doing. We take a temporal network, we construct a distance matrix that we input to a reduction method, and we take just the first principal component and obtain the low dimensional network trajectory that we hope that it has the same properties of the temporal network. For example, if the temporal network is periodic, we hope that the time series of one-dimensional time series is periodic. If it is chaotic, we hope that this is chaotic, okay? Well, we hope that it inherits the dynamics of the temporal network. So how are the results assessed? Well, for example, if we take the final thing, the result, the low dimensional trajectory, which is just a time series, we compute the autocorrelation function, which is just a measure that, well, tell us that there is some periodicity or temporal dependencies in that embedding, in that low dimensional embedding. And our ground truth will be computing the network autocorrelation function, which is the same, but using the network, okay? And well, we will just compare the ACF and the network ACF to assess the results. And when we have chaotic temporal networks, we will use the maximum Lyapunov exponent, which we know that it estimates sensitivity to initial conditions. That means that somehow the two nearby trajectories diverge in the phase space, right? So that is how we will assess the results. Now I'm going to show you 3 results using synthetic temporal networks. That means that we are using temporal networks that we know how they behave, so we can somehow test our method, and then we will apply this to some 2 real data sets, in fact. So first we will start with predict temporal networks. we will just build 500 snapshots with 20 nodes each, just to as a proof of concept. And we will the dynamics of the links are built like cosine with some asynchronous behavior and some extrinsic noise. And as you can see, when the standard deviation is equal to 1, the dynamics of the link somehow reflect that 100 is the original period, which is okay. But when we increase the noise, the extrinsic noise, we see that, well, there is no period in the links. We cannot observe that. But doing the embedding, which is taking this object that is the distance matrix I told you before, and making an input into PCA and just abstracting the first principal component, we see that both scalar embeddings filter the local noise and act as the noisers. So this is very interesting to me because, of course, this was not expected at all. So in fact, it amplifies the periodic backbone of the signal. If we now use the DARP model, that discrete autoregressive network model of with memory order P, which you may say, what is that? But it is something that builds temporal networks that have a network KCF of this form. It is flat when the lag is lower or equal than the memory order, and it has an exponential decay when tau is larger than P, right? So this is, again, the famous embedding, which, well, it does not tell us anything, but if we compute the ACF from that embedding, we see that the ACF, well, it follows the same structure the network ACF. So scalar embeddings inherit that memory structure of those temporal networks. Now, if we take chaotic temporal networks, and well, this is interesting because we use an idea that my tutor Lucas da Casa somehow come up with, that is the dictionary trick, which is a really good idea. I do not have time to explain with detail here, but I encourage you to ask me or to read our paper, because it is a good idea that it simply just takes, in this case, the fully chaotic map, a given function with a prescribed dynamics, and it builds a temporal network that will inherit that that dynamics. Okay, in this case, chaotic, and with Lyapunov exponents of natural logarithm of 2. So, well, when we do again all this procedure of building a distance matrix, then that is the input of the PCA, then the embedding. When we take the difference between two nearby trajectories, we observe an exponential divergence of the slope in the logarithm axis of exactly the Lyapunov exponent that we have been studying. So they preserve chaotic behavior. If we apply that to a real data set, that's the email Democratic National Committee, which is a periodic committee in which, well, funny enough, this is an email data set that you can find in social patterns, and it depicts how politicians interact with each other via email during that month. Sorry. Well, it has a 7-day periodicity, which of course means that politicians mostly work on Mondays after the weekend is already gone. But then well, the embedding, well, more or less suggests a 7 days period, but the ACF that amplifies that periodic backbone actually reflects what we know about the network ACF, that, well, it has a period of exactly 7 days. And if we now use another social pattern data set. In this case, it's a primary school in Malawi, I think, in which we take 9 hours. I think it's from 8 or 8:30 to 5, something like that. And we have 243 children notes, and over 1,300 snapshots. We see that, well, it preserves the memory it should have, because the characteristic time scale is, as you can see this when it drops, is more or less 120 snapshots, which that corresponds to 47 minutes, which match class duration. So, and another interesting take here is that, and it reflects the idea, we have 200 nodes, let's say. So the agency matrices are 200 times 200. That means is 400,000, right? The number of entries in those agency matrices. So we have reduced all those numbers to just one scalar. And the funny thing is that the first principal component, the scalar embedding, actually captures over the 92% of the variance. For me, that's amazing. I mean, just considering the big truncation that we did with the PCA, all the information we have left, that's impressive. So we have seen that if we focus on the relative distances and the difference between snapshots, not in centrality or not in the properties of each node, we found that scalar embedding captures the main properties of the temporal network. Of course, as I said, this is just a proof of concept. We have just focused on scalar embeddings to see where we can get, right? But it's easily generalized to larger dimensions, because we just truncate it at one principal component, but you can use 2, 3, or more. Okay, but we do that because we can plot it, we can very easily understand it, and for future work, this is. I know that there are people here that are working in this, so I think that the future is more than short for them, for this line of work. And well, you can use other than Euclidean distance, and you can consider, I think that is called TDK networks in literature. That means that closer snapshots are more important than snapshots that are very apart in time. And well, applications of this are basically because we now have time series. So we take our toolbox of time series, and we can use whatever we want. So, for example, time series forecasting, this is a way people are trying to forecast stock prices, for example, limp prediction on our modeling, right? And well, to sum up, this just offers a new way and to explore complex systems by using temporal networks, by transforming them into time series. And well, I just want to thank you and Nifibe for me being able to be here. And well, thank you very much for your attention.
Thank you very much. That was really interesting. Any questions? The questions over there. I was thinking, is there something special about the principal components? Or could you use some other feature? Like, where's the sort of the magic of the system, of this approach coming from?
Okay, what is magical? I mean, somehow when you use PCA and you take just the PCA gives you principal components that are the directions in which the data somehow explains the most variance in data. So the first principal component is the component that explains most of the variance. I'm thinking about what Luis presented yesterday about the power law that really has a line on it. But what is special? It is just the component that explains somehow the most in a linear fashion. That is, PCA is a linear method.
Have you thought of using any other sorts of dimensionality reduction?
We used, in fact, in my master thesis, we use classical multidimensional scaling, which is more or less is a cousin of the PCA, but it sees the similarity between snapshots in this case, not the most variance, not as compared to the PCA. So they are much alike. In fact, I think if any mathematician puts into work, I think they can find the mathematical connection between. But for us, being pragmatical, they throw us the same result.
Any other questions? If there are no more questions, thank the speaker again. Thank you.
O sea, que tienes que conectar el esto, ¿no? ¿Dónde está? ¿Desapareció? Ah, no. ¿Sí?
Hola, hola. Probando.
Okay, so the last speaker of the session is Rubén Calvo Ibáñez, representative of Granada, and he's going to be talking about frequency-dependent covariance and the critical brain.
Yeah, so I'm Rubén Calvo Ibáñez. I'm doing my PhD thesis with this very good-looking man here, Miguel Ángel. I'm trying to get a rise, so I have to really be encouraging. And well, yeah, I'm doing a presentation called the frequency-dependent covariance and the critical brain. That was going to be the topic of the presentation, but then I added some highlights at the end, so we're going to talk about a couple of things more. This is going to be my index that I'm going to follow. Let's start with a short introduction. So, recent technological advances have enabled scientists to take a closer look into the human and animal brain. Non-invasive techniques such as fMRI, EEG, or MEG now provide us with great detailed information with great spatial in the case of fMRI, and temporal in the case of MEG and EEG resolution. On the other hand, microscopic dynamics can also sometimes be inferred using invasive techniques only allowed in animal-like mice that provide simultaneous recordings of thousands of cells, meaning that we have a lot of great quality data in the brain, but can we use it to understand exactly how it works? And let me talk you a bit about the critical brain hypothesis. Many of you might have heard about this. So, we as physicists are tempted to study the brain using tools from statistical physics and discernment systems. Indeed, the brain is composed of thousands of millions of smaller units called neurons that cooperate together in a perfect way to achieve a specific goal: the processing of information and the elaboration of proper responses. Now, if this is the case, then all these small units can operate together in many different ways. For example, they could all decide to fire together, leading to a completely synchronized regime, or otherwise they could decide to ignore each other and fire whenever they want, leading to an unharmonious regime of chaotic activity. A widely discussed conjecture establishes that the brain could extract significant advantages from operating close to a critical point, and in between the completely chaotic regime and the completely synchronized regime. So, we have plenty of data, and we have a hypothesis, namely that the brain is critical. Now, how can we test that? What tools can we use to infer the distance to the critical point? Well, what our research group proposed is to study the hierarchy of functional modes. See, time series that are critical are a mixture of many dynamical states, some of them ordered, others lacking any particular structure at all. And, well, if we want to decompose our time series into a set of independent dynamical states, we can use principal component analysis. If the system was to be completely ordered, then only one dynamical mode would be predominant, and the spectrum of principal components would look something like this. On the other hand, if the system was to be completely disordered, the spectrum of principal components would be completely flat, as all dynamical states are somehow present. But what happens at the critical point? Well, close to a phase transition, the system develops a power law, signature of scale invariance. This means that there is a vast repertoire of close to critical functional states. This is the power that I was talking about. Comparing this power law with the so-called Huon-Somponinsky distribution, we are able to infer a parameter g that measures the distance to the critical point, with g being close to 1 whenever the system is about to approach the critical state, and g being equals to 0 whenever the system is at the disordered phase. I'm going to introduce now this frequency-dependent principal component analysis method that we developed in our article. And the thing is that principal component analysis does not take into account the temporal structure of the data because it relies mainly on studying the same time correlation. In many biological systems, and in general in many out-of-equilibrium systems, time plays a crucial role. Now, take these two neurons as an example. It is clear that the same time correlation between them is 0, because whenever one of them is on, the other one's off. However, there is a clear correlation structure in time, namely that some delay tau after one fires, the other one will fire as well. So we went a step further and developed a new method to analyze principal components at different time scales. Let us illustrate it with a very simple example. Consider what? No. So as I was saying, in order to illustrate our method, we are going to consider a very simple example in 2 dimensions. This is the stochastic process that I'm showing on the screen, which is a mixture of a Gaussian process that will create these blue dots that are anticorrelated and distributed along the blue ellipsoid that I'm going to show on the screen in just about... there we go. We're going to add this deterministic signal right here that oscillates with a periodic frequency omega sub 0 around the right trajectory. When added together, these two processes produce the stochastic processes that I'm going to show on the screen there, where one can distinguish by the existence of a characteristic oscillation. Now, again, just to refresh, I will show you in blue the stochastic process and in red the deterministic trajectory. If we were to blindly perform principal component analysis, we would see that the principal components that I'm going to show in white do not align with either the deterministic signal or the stochastic process. It mixes information coming from both sources. When we apply our methodology at the longest time scales, 0 frequency, the characteristic signal just vanishes and we are left with the contribution of the Gaussian process. On the other hand, at the characteristic frequency, we recover this deterministic signal. And because this technique works in the complex plane, in general, principal components are no longer linear manifolds, but rather curves. So we're able to disentangle these two independent sources of variability just by filtering out the appropriate timescales. But, uh, but let's get back to what our main interest was, which was the brain, right? So for getting back to the human brain, we want to apply our technique to a dataset composed of MEG time series from control subjects together with Parkinson patients. First of all, we take our time series and decompose it into individual frequencies by means of the Fourier transform. Once we have this stochastic process in the frequency domain, we can calculate correlations among pairs and look at the hierarchy of principal components. We get a very broad spectrum that can be well fitted to the Huang-Polisky distribution to infer the distance to the critical point at each particular timescale. We found a very broad spectrum that can be well fitted, and we did this and got that for the control subjects, the most critical frequencies was the slowest timescales together with the so-called alpha band, an interval of between 8 to 12 hertz. On the other hand, the presence of pathologies like Parkinson has a great impact on this behavior. Now there is no longer a clear peak at the alpha band, but rather there is a vast repertoire close to critical frequencies. Let me just say that these differences could not have been uncovered just by looking at the slowest timescales as previous works have done, because the behavior of the system close to omega equals 0 is practically the same in both groups. Okay? Furthermore, our tool also allows us to take a closer look at the spatiotemporal patterns or principal components at each particular band. It's working. These patterns are much like the different notes played by a string in a violin. The first harmonic, or the dominant note, is the most important one, as it's the one that explains most of the variance. It's as if that particular note was louder, following with our music metaphor. Just as a comparison, let me show you how these notes look like in an actual brain, compared with the strings of a violin. Just like it happens in the strings, the principal harmonics tend to look simpler, with following ones appear a bit more complex. Now, coming back to our previous discussion, these first spatiotemporal patterns or dominant notes have striking differences between the control subjects and the Parkinson patients, where there exists a higher level of symmetry. This technique hence proves that that this particular disease has a huge impact on the way that the brain transmits information across different timescales. Following with our music metaphor, it seems as though the brain of a diseased individual needed to be tuned back to the original key to produce the desired sounds, right? So, just summing up some take-home messages. In short, we have proposed a new technique to investigate timescales beyond the slowest ones, namely the frequency-dependent principal component analysis, or for short, FDPCA. Plus, we have applied this methodology to a dataset composed of healthy control subjects and patients with Parkinson's disease. Our results point that there are striking differences when observed through the magnifying glass of our framework, differences that could not have been uncovered otherwise. Not only the distance to criticality was found to be very different across subjects, but also the main spatiotemporal patterns or the main nodes that the brain displayed. So this would be the end of my speech. If I hadn't realized that this was going to be a 30 minutes presentation, so I added another presentation on top of this, and I'm going to tell you what we are working on right now. So, so what are we working on right now? In short, how the dynamical behavior of the brain changes when you look at it with a different time resolution. We first scanned brain activity across frequencies and saw patterns that looked like a system on the verge of a phase transition, pink water just about to boil. Now we're asking, do those signatures of criticality still hold when you zoom in and out in time? This matters because brain data comes in very different scales, from millisecond spikes in single neurons to local field potentials unfolding over tens to hundreds of milliseconds, all the way down to slow oxygen level dependent signals that take seconds. We are testing whether the same near critical fingerprints show up across all these different time resolutions. To test this, we use a classic physics tool called the renormalization group, basically the math of zooming. It asks, how do the rules of our universe change when you change the resolution? That's why everyday motion looks Newtonian, even though deep down nature follows quantum physics. When you zoom out, messy microscopic details just get averaged away and only the important stuff survives. That's why you don't need the speed of every molecule to know a room's temperature, you just need the collective behavior. It's a bit like art, actually. If you press your nose against a Van Gogh, you only see brushstrokes. Now step back, and the whole picture will emerge. In statistical physics, this tool also tells you how close a system is to a phase transition. At a critical point, something very special happens. The system becomes scale invariant. Zoom in or out, and the same pattern will emerge. That's exactly the kind of signature that we are hunting for in brain activity at different time resolutions. The simplest way that we can zoom out with a normalization group is by averaging neighbors, what physicists call coarse graining. Think back to the Van Gogh example. If you squint, the brushstrokes blur and the composition appears. We do the same with data. We take a small region, we combine the values together into one and then repeat. The fine details fade and the large scale appears. What's a cut? Well, the thing is, in the brain, distance is not equal to similarity, right? Two far apart neurons, like this one, can be totally in synchrony, while the close ones might be doing totally different things. So instead of averaging by where cells are, we have to average by how they behave. We group together signals that are highly correlated, they rise and fall together, and coarse grain those. This behavior-based zooming is the essence of the phenomenological renormalization group. We applied this behavior-based zooming to neural activity right on the edge of a phase transition. Inside each group of neurons is clustered this blurred out version of a group of neurons. We measure three different things: the hierarchy of principal components, how the main activity patterns stack up, the overall size of the fluctuations of the neural activity, the total variance, and how long the activity stays similar before changing. That's called the correlation time. All of these three quantities followed clean scaling laws with the size of the coarse graining. The principal components fell off as a power law with a power exponent, mu, the variance scale with alpha, and the correlation time with zeta. In physics, these exponents act like a system's fingerprint. They label its universality class. Now here's the twist. We showed, both on paper and in simulations, that these exponents aren't fixed. They change with the time resolution that you use. Change how much you coarse grain in time, and you get different critical exponents. In other words, spike trains and oxygen level dependent signals don't exactly follow the same scaling laws. What surprises most is a tight mathematical link between time resolution and the inputs that a neural network receives. See, neural circuits turn stimuli and the inputs into information. But we found that how finely you look in time is equivalent to changing the temporal structure of those inputs. Using a finer time resolution acts like driving the network with inputs that vary rapidly with a shorter correlation time. Coarse graining in time is equivalent to inputs that vary slowly with a longer correlation time. Think back to the painting. That's going to be our input. Now imagine two different cameras. I'm going to catch my breath so that the video has time to get to me. Now imagine two different cameras. One is perfectly sharp, the other one blurs. Here's the point. A blurry painting photograph with a normal camera is the same as a normal painting photograph with a blurring one. The same, different inputs and different sources of the blur. Now, since input statistics can strongly shape the critical exponents that we measure, we have to ask, when experiments report near critical behavior, how much is inherited from the temporal structure of the inputs and how much is intrinsic to the real dynamics of the brain? So, we stress tested this idea on the simplest network possible, neurons with no connections at all, each one independent. We take this and get a network with independent connections. We drove this network with inputs whose correlation time we could dial from fast to slow, and mimicked real experiments by analyzing short recordings on the order of minutes. To our surprise, this uncoupled system produced similar scaling exponents mu, alpha, and zeta as a network genuinely near a critical point. Translation: input the statistics and finite recording windows can mimic near critical fingerprints. Oof. Drama. I'll be honest, this kind of freaked me out. I'm doing my thesis on the critical brain hypothesis, and for a moment there I thought, great, so everything I did was wrong. Well, yes and no. First, what was off? I've been working with fMRI datasets, which are about 50 minutes recording with a correlation time of about 10 seconds. With that combo, theory says that you are in the danger zone. Finite windows plus long correlation times can fake criticality. So I ran a sanity check. I randomized the time series, basically shuffling them. That keeps all the temporal structure of the data but kills all possible correlation among pairs. If the critical signatures survive that shuffle, they are likely spurious. I did this, and drumroll please. Yeah, I get the same results after reshuffling. Luckily for me and my thesis, that wasn't the end. By treating each participant as an independent realization, I could pull samples. 50 minutes per person across 136 participants took me to about 34 hours of data. That pushed us well outside the danger zone. When I randomized this pooled dataset, the critical signatures vanished, which means the originals weren't spurious. Then what's the takeaway? Well, with fMRI, you usually can't make strong claims about criticality at the single participant level. The time series just isn't long enough. So whenever you see a paper doing that, be skeptical. Remember that even independent processes with long correlation times can mimic near critical behavior. Thanks for your attention. I'm gonna leave here these videos that are on my YouTube channel in case you wanna revisit any of what I've been talking about. And this is the articles that we have written. This a list of my collaborators. So thank you for your time.
Thank you very much. Any questions? Any critical questions? Not too critical.
Thank you so much for the talk. Really beautiful slides. I have a,
Thank you.
I have a question about how you interpret some of these signatures of criticality in this frequency-dependent way. So, thinking specifically about part one.
Okay.
Correct me if I'm wrong. It seems to me that when we talk about criticality and power laws, typically we have in mind something like a system with a control parameter that
Exactly.
you tweak to some particular point, and then poof, at that point all the good stuff happens and you get the power laws and
Yeah.
everything. And then we make a measure of criticality, that is, how close are you to the power. It seems to me that the way your analysis kind of was motivated was by actually let's focus on the power law itself and let's see if there's any kind of frequency at which the covariance looks like a power law. But in doing that, it seems we have swapped what we really cared about, which is criticality, to with that power law, which is a signature but not the real thing, quote unquote, right? So I wonder, is there something like a generative process that's actually going on at alpha that he can tell, that he can say confidently is at a critical point?
So if I'm understanding correctly, so what you're saying is that whenever we do this, we are estimating this parameter G, which is like a one-dimensional thing where you tune like the size of the fluctuations of the synaptic links, and it's a bit like maybe too simplistic. And basically the whole signature that we are looking for is this kind of power law thing in the spectral principal components, right? And you are kind of like saying to me like, is this the whole story, or is that what you are trying to ask me, or?
Roughly speaking. So let me be more precise.
Okay.
When you say that you have this kind of broadband fMRI, broadband MEG, or EEG signal, you do your frequency decomposition and you look specifically at 10 hertz, and you say, at 10 hertz I have a G of 0.9.
Exactly.
Can you then tell that there is a actual, like a real underlying generative process
Okay,
at
that
10
could
hertz
generate that
that
G.
is at the boundary between an ordered and a disordered phase?
Okay. Yeah, we can do that. Like we can build specific matrices, like with some simple rules, so that you get, for example, that the most critical frequency is that one. But we like I didn't put all the details here, but you can read the article. We didn't only just look at this parameter G, which measures basically, like roughly speaking, how broad the distribution of principal components is. We also look, for example, at this dimensionality, which is like this inverse participation ratio, which kind of collapses whenever you approach a critical point. We got the same results, and then we built this very simple model in which you have excitation inhibition, and you so basically what this does is that it's going to shift. For example, you have in mind the typical spectrum of eigenvalues of a random matrix, like a circle law, right? Well, what introducing excitation inhibition does is it usually shifts this into like something that is curved, so that there exists a particular frequency at which this can oscillate, okay? Because it's going to have like a hop bifurcation. So basically, that kind of mechanism can create the same, or at least similar, patterns of distance to criticality at different frequencies as the ones that we observe. Is that what you are asking?
I'll pick your brains later. Thank you.
You're welcome.
Any more questions?
I just wanted to know if you thought about when you say you define a coarse graining for how you group things together. There's this issue that neurons that are nearby, for example, might not be as similar. So maybe renormalizing or coarse graining in terms of distance is not such a good idea. But have you tried, and do you have an intuition of what might happen nevertheless, even if that's not a good idea?
I guess, like for example, if you do it in random networks, you're not gonna see anything, right? Because like basically the topology is just completely random. It's not embedded on a particular geometry. But if you do it, for example, in fMRI datasets, I think you would get basically the same, because correlation is going to be really affected by where you are, right? Because the brain has a particular geometry, and it has a particular, like the correlation sometimes basically inferred from the geometry that you have, right? That's the reason why you can make like an artificial connectome just by putting connections that decay exponentially with distance, right? So you're gonna get the same, but with like at the macroscopic level, that's probably not gonna happen. I haven't tried, but in this paper in particular, we haven't analyzed microscopic recordings, just whole brain thing.
Any more questions? If not, well, thank you very much,
Thank
Ruben. And before, oh sorry, go ahead. So before you go, before I made the false claim, which was that Ruben was our last speaker, but actually I thought there were no more speakers. But we do have another speaker because there's been a change in the timetable. So now we have Rafael. If you want to start in some way. And before I forget, there are three people who are vegetarians, and when you go to the dinner tonight, the gala dinner, you will need a little bit of paper which says that you're a vegetarian to make sure that they give you the right food. And so those three of you should afterwards go and ask the lady outside for these tickets. Okay? So you'll know who you are. The three people who are vegetarians, please go and ask afterwards for a little bit of paper before you go, and make sure to have it for the gala dinner. Yeah. So it's just outside here, the little table here. Yeah. Okay. Okay, so thank you. So the actual last speaker of the session is Rafael Uceda, and he's going to be speaking about illuminating chiral molecular design guided by data science, Edison derivatives for CPL emissions.
So thank you.
Thank you. I'm Rafael García. I work here in Granada in the Organic Chemistry Department, and I will present you this topic that can be summarized in how to use data science for molecular design. We, the chemists, prepare molecules. We, the organic chemists, prepare new molecules for different reasons. One obvious reason is their usefulness, and for example, we prepare different drugs like Taxol, which is a very powerful anti-cancer agent that is very scarce in nature. So we develop new recipes to prepare large amounts of Taxol. Other interesting applications are OLEDs that are present in every single screen nowadays. And we also prepare molecules to their beauty or their appealing geometries, such as infinity, cubane, or complex helicase topologies. In any case, we have the techniques to prepare new molecules. But the main question is, what molecules should I prepare? The full chemical space comprises around 10 up to 60 molecules. Just let's see pentacene as an example. Pentacene is commonly used as a semiconductor and has 14 different positions. If we include up to 4 groups in the 14th position of pentacene, we have up to 10 up to 8 possibilities, the number of stars in a galaxy. If we increase the number of groups up to 8, still a very small number, we have 10 up to 11 possibilities. If we move to 30 position and all 500 substituents, now we have nearly 10 up to 80 possibilities, the number of atoms in the universe. This one is obviously a metaphor, but the main message here is whatever the property you are interested in is, you have to deal with an incredibly high amount of probabilities and possibilities. So we need to study the problem carefully. In our case, our base areas are the chemical reasoning and the intuition, but maybe we need something more, considering every problem. In our case, we are interested on chirality. Chirality is a property of an object not being identical to its mirror image. The terms come to the Greek hands because the hands are already chiral. An sphere, for example, is a chiral because it's identical to the mirror image. Nature typically chooses chirality, and for example, more than 90% of the cells turn to the right. In the same line, all the amino acids in our bodies are chiral and they have the same chirality. Same can be said for DNA. And the two hands of chiral molecules, the enantiomers, can have very different properties, such as smell, flavor, or pharmacological properties. The chiral molecules can interact differently with other chiral entities, such as our own bodies. Or light. Light can be circularly polarized, so we can define left and right circularly polarized light. Light can be chiral. Typically, molecules absorb or emit normal light, and we recover normal absorbance or fluorescent spectra. But if we move to chiral molecules and chiral light, we enter in the world of chiro-optical properties. Then we have the chiral absorbance, electronic circular dichroism, where one enantiomer absorbs more left than right and the other one absorbs more right than left, giving us a spectra with positive and negative things. For both enantiomers, we have the same profile, but with opposite signs. Also, we have the chiral fluorescence, the circularly polarized luminescence, where a chiral molecule is able to emit in a pure chemical way circularly polarized light. These techniques have received a lot of interest in recent times because this chemical generation of CPL, circularly polarized light, can be used for many purposes, such as chiral synthesis, chiral encryption, or the development of more efficient OLED, such as circularly polarized OLEDs. All these applications have the added value of chirality. I have said that in circularly polarized luminescence, we have a net circularly polarized light. That is the result that more left than right or more right than left. But the main question is, how much is more? We need to define the signal, typically as a subtraction, and we also need to define the actual dissymmetry of the process using the dissymmetry factor G, called Gx for absorption and G lum for emission. This adimensional value range from 0 for chiral samples to 2 or -2 for pure circularly polarized light. These are the experimental definition, and these are the theoretical definition, where G is understood in terms of the magnetic and electric moment of the transition. We also need to present the rotatory strength R, also described in terms of these vectors, and that is the height of the signal. R is very important for many different purposes, such as sensing. This G, although having an upper limit of 2, typically range for simple organic molecules in the range of 10 to -3 or even -4, and the molecules that exceed the limit of 10 to -2 are quite scarce. So the question is, how can we achieve these exceptional properties? How can we achieve larger dissymmetry values in order to use these compounds in the previous applications? Chemists, using the organic reaction, have studied many different scaffolds, and one of the most important ones are the helices. Helices are these helical compounds composed by phenyl rings. They are like molecular screws, and they have a defined chirality beyond 6 rings. So the most important member of the family is the 6 helice, and the simplest one. They have been studied under different approaches, such as symmetry, p-extension, substitution, expanded helicins, or other physically guided approaches like substitution to modify the transition moments, or increasing the inner area of the helix to increase the moment, the transition moment, the magnetic transition moment. Remember that even that this is a very complex problem. Even with the simplest helicine, 6 helicine, with 16 position, and just considering 4 groups, for example, the halogens, fluorine, chlorine, bromine, and iodine, we move in a space of millions and billions of possibilities. This number of combination hinders the development of structure-property relationship that are quite valuable for the development of new compounds. These relationships only appear when we have a higher amount of data. Nowadays, we can compute the optical properties as, for example, circular decreasing spectra using DEFT in just hours. But it's still hours. To understand the chiroptical problem, we need more data and we need them faster. Machine learning can be a solution here. Using machine learning, we could at least predict the maximum responses of the circular decreasing spectra, which are very useful for sensing, for example. And with millions of data obtained by machine learning model, we could understand the chiroptical phenomena and answer a question like, which is the maximum value for rotatory strength in a halohelicin? 100, 1000, 10,000? Nobody knows yet. So this is our first problem, using machine learning to study the chiroptical response of halohelicin. We built a data set using DEFT calculations. Why? Because this methodology ensures that all data are comparable, and it's very easy to obtain more data. We just need to compute them. We chose the helicin randomly, so they cover all the full range of Earth. Using this protocol, we compute helicin with up to 4 halogens. And since all them have a very similar structure, we decide to codify them into a vector of 16 numbers, where each number codifies a position of the helicin. Once we carry out the simulation, we build the neural network model, and we saw a very good statistical marks, and we were able to predict air in all the range of the property with accuracy. But the main problem here for us is that chemists love intuition. We work by intuition and we prepare new molecules by intuition. And this kind of models typically works like black boxes. So we decided to build a simpler model called one body model, where the air of a given halohelicin is computed just taking into account what substituent we have in every single position. For example, One bromo, 6 helices. Bromine in position 1, and nitrogen in the rest of position. This model is obviously worse than the previous one, but now we are dealing with 40 parameters instead of nearly 10,000. And these 40 parameters can give us a lot of physical information. There are some positions, 2 and 3, and some halogens, bromine and iodine, that increase the critical response. And even more importantly, these are the only combination that increase the critical response. So now we are predicting and parameterizing the air in alloys. In any case, now we have a tool, a model on hands to predict air in alloylysine in just seconds or milliseconds, so we can evaluate all the possibilities. The distribution of air are quite similar to the dataset, and when we look at the best derivatives, those that with air exceeding 850, we see the same pattern that the one body model suggested. Bromine and iodine in position 2 and in position 3. These one are the same by symmetry. At this point, we have studied lysine up to 4 halogens, but we were ambitious, so we decided to move up to 6 halogens, moving from thousands of combinations up to millions of compounds. Obviously, we need to expand our dataset, including data with 5 and 6 halogens. But this is one of the best parts of our protocol. If we need more data, we just compute them. We have the thing. After doing that, we develop again the model, and we evaluate all the possibilities up to 6 halogens. Again, very good models, very good statistical parameters, and same conclusions appears. So we have been able to reduce a very complex problem of millions and billions of compounds into this simple picture, where we have positions that increase air and positions that reduce air. Following these simple rules, now we can design ex professo exceptional lysines, normal lysines, or lysines with poor critical responses. Obviously, we are interested on the first group, those ones that have bromine and iodine in position 2 and in position 3. And this one is a very small group, less than 100 compounds. So we can study all of them carefully with the T. After doing that, we achieve tetrabromoelysine as a privileged scaffold with an air of 943, far beyond the pristine 6 lysine and beyond the best data in the dataset, so the model is extrapolating. This compound was selected among 10 up to 10 possibilities, and the high value can be explained in terms of the magnetic moment of the transition increased due to the presence of bromine in this position. So by far, this is the best compound, but we have studied lysine up to 6 halogens. What happened with 7, 8, 9? We decided to apply our models to lysine with more substitution. So we compute 100 lysine for every type of substitution, and we apply then the model, concluding that our models, trained with data up to 6 halogens, are valid for larger substitution, at least for the range of air. So we can use them to see if there are some lysine better than tetrabromo. After doing that, the results are quite clear. Substitution beyond 6 halogens is detrimental to critical properties. For example, here, for fixed 16 halogens, we evaluate 1 million candidates. The best one had an air of nearly 600. So the best derivatives are those with 4 substituents, with bromine and iodine in position 2 and in position 3. And among them, the best predicted candidate is 2, 3, 14, 15 tetrabromoelysine. At the beginning, I said that chemists know how to prepare molecules, but they don't know what molecules they should prepare. But now we have a very good candidate, tetrabromo. So we decided to prepare it. We did it, and we prepared it along with dibromo as a reference. This is the most chemical slide of the presentation, and this is the synthetic path of the route. It's very straightforward, it's very simple, and we achieve both products along with an X-ray crystal for tetrabromoelysine. After carrying the synthesis, we measure the circular decreasing spectra. We have tetrabromo in red, the bromo in black, and we see a very good agreement between experimentation and theoretical results. So, to sum up this part, we have been able to predict, parameterize, and understand the maximum rotatory strength R in allohelicin, a family of 10 up to 10 compounds, and we have been able to found and prepare the best derivative among them. What is next? Well, we have studied the maximum and the minimum rotatory strength in the CD spectrum. We can think also in the wavelengths, the energies of the process. And also, we can think in the first transition, the process that goes from the ground state to the first excited state. Why? Because in rigid organic molecules, this process is quite similar to the emission process. So we can use this transition, the first one in the CD spectra, to study the chiral emission, the chiral fluorescence, the CPL, the valuable CPL. So we also study the rotatory strength, the wavelength, and the physical parameters of the transition, electric moment, magnetic moment, and the symmetry. Along with the increase of properties, we want to expand the chemical space, not covering just halogen, but also donors of electrons, acceptor of electron, and neutral carbon-based group. So now we can cover all the full chemical family. Remember that each family, for example, helicin with just halogens or helicin with just acceptor, has a size of 10 up to 10, more or less. And if we combine all the 16 positions of helicin with the 16 groups, we move to a space of 10 up to 18, more compounds than sequence in the universe. So we are in a very complex problem. Also, we should remember that less than 400 helicins have been described in the literature because the synthesis is very difficult. The synthesis takes a lot of time and resources. So we should be sure before trying to synthesize them. As an example, I will present the symmetry factor for the first transition and our known halogens. The first results were so awful and disappointing. In the test subset, we have an error square or 0.01. The model doesn't learn anything. The model doesn't predict nothing, and the model doesn't extrapolate nothing. In fact, the results were so disappointing that we thought that maybe we were trying to modulate different things at the same time, and maybe we have some different physical phenomena at the same time. So we moved from a global model to a local model where we have our data, our helicins, and once we want to ask for a new compound, we develop a local model trained with the nearest neighbors. This approach ensures us to catch the physical behavior of this compound. This approach gives the following results. For the first transition, we have the rotatory strength, the wavelength, and this is very important because these points are quite different to the majority of the points, and they are very difficult to model, to predict with accuracy without the local approach. Electric moment, magnetic moment, the symmetry factor, maximum rotatory strength, its wavelength, the minimum, and the wavelength. So all the full circular decreasing spectra. In this moment, we are able to predict up to 9 properties in millions of compounds that cover the full chemical family of helicin, one of the most important families in optical property. But we can use this model for a lot of things, and I will show you several examples. I have defined 2 different modes: predict your helicin and design your helicin. In predict your helicin, we can think in the CD spectra, for example. Typically, CD spectra is computed using DEFT, where we compute the vertical bars, and then, using a program, we put a Gaussian distribution. So we have the computational circular decreasing spectrum. In this work, we have 3 transition bars. The first one, the most positive one, and the most negative one. So we can try to predict the full circular decreasing spectra instead of pure numerical prediction. And we have some candidates. Dibromo and tetrabromo. We have the experimental circular decreasing spectra. We did it, and these are the results. With just 3 transitions, we are able to predict the full circular decreasing spectra in good agreement with the experimental results. Other interesting cases are the Elisyn with fluorine atoms. Panda and collaborators have studied the effect of terminal fluorination in Elisyn, including 2, 4, and 8 fluorine atoms. They conclude that the circular decreasing spectra is very similar in every single case, with difluoroelisyn having a slightly more intense signal here. These are our results, with this high level of detail. And even more importantly, now we are predicting an Elisyn with 8 groups. Even our dataset comprises data up to 6. So we are extrapolating and going beyond our own dataset. Talking about design your Elisyn, this is a very important part because more than the statistical metrics, our model will be considered successful if they tell us which molecule we should synthesize. If we join our model, our local model, with genetic algorithm, we can generate a random sample of Elisyn. We can compute them with the local model. And after different generation of mutation, we can approach a specific value of a target property. So we can define new Elisyn with specific properties. As an example, I will show you the wavelength of the first transition. First, we ask for 100 nanometers. This is a very populated area of the distribution. So we found different derivatives, even with 7 substituents, going beyond our 6 groups in the dataset. Little more difficult. 400, 4 substituents, just 4 substituents, and symmetry, thinking about synthesizability. Remember the tetrabromo. Again, we have very good results when comparing the candidate proposed with the DEFT values. Even more complicated. Now we ask for 600, an almost empty area of the distribution. This is the nearest candidate so far, but we can include this data in the dataset and refine the genetic algorithm along iteration. So along different iterations, we can achieve the desired value for the target property. And talking about designing Elisyn, we need to speak about designing CPL emitters. CPL emitters relies on the first transition. So we must design these parameters: electric moment, magnetic moment, and the symmetry factor. A good CPL emitter must meet different criteria at the same time. Electric moment must be at least 1. So we have imposed 1.5. Magnetic moment as 1 is a prototypical value. And G should be as larger as possible. But typically, for simpler organose molecule, it has a value of 10 up to -3. So we ask for 10 up to -2 as an exceptional candidate. Also, we ask for symmetric tetra-substitute Elisyns, thinking again in synthesizability. The model gave us some candidate, and again we see a very good agreement between machine learning values and DFT values. So in just an hour of iteration of the genetic algorithm, we have been able to found easy to prepare 6 Elisyns with different difficult criteria at the same time. A work where a chemist, a conventional chemist, will spend months or even years. So as a conclusion, regarding air in allo-Elisyn, we can say that employing just 1,000 DFT data, we have built machine learning models for predicting the properties in 10 up to 10 molecules. Although the most complex model always gives the best correlation, a parameterization of air mass acquires evident physical meaning when we use simpler one-body model. And in this line, we have found an structure property relationships where we have position and halogen that increase their value, mainly bromine and iodine position 2 and position 3. And finally, the prediction has been experimentally supported by the synthesis of 2 of the best predicted candidates. Expanding to 6-lysine, the use of local models allows us to predict up to 9 properties with A in 6-lysine with any type of substitution, an important space for billions of compounds. The models go beyond the pure numerical prediction and provide insight into different optical phenomena, such as the full circular decreasing spectrum. And by combining local models and genetic algorithms, one can obtain candidates with specific properties, and at the same time identify those candidates that have straightforward synthesis. So one main result, as a main conclusion, we can say that this work shows the potential of the T calculation along with artificial intelligence techniques to advance in a problem as complex as the search for materials with exceptional properties. Finally, I want to thank all my collaborators, especially my supervisor, Professor Juan Manuel Cuerva and Professor Antonio Mota, and all you for your kind attention. Thank you very much.
Thank you very much. Questions?
Yes, very nice talk, Rafael. So I have a question, maybe it's related with some other talk that has been done previously. So in this huge space of possible structures for this Ellison you can build, it's so huge. So all the structures are stable. I mean, it will happen that some possibilities you can build or you can design, maybe you need, after some times, can go to another one. So it's real so big this space.
Not in principle. Maybe the molecule, the final molecule, will decompose into other things, but not into another Ellison. It will be difficult. But in any case, we don't know if a product is stable until the moment we prepare it. So, and of course, not every single Ellison has the same difficulty, the same degree of difficulty to prepare.
No.
The symmetric one, for example, easier.
No, I was asking this because, for example, if you design or use different molecules, I was thinking in a part of the DNA, for example. DNA, we are saying about DNA. We are heard a talk about how there's a phase transition between very simple proteins to another proteins. So then my question is if maybe they are in this whole space, for example, if you go to more complex molecules, then maybe this space is not so big. You understand?
Not so big.
So large. It's not so large. When you go to more complex molecule.
Maybe, but in any case, we are dealing with millions of candidates. And even more importantly, we want several properties for application, but we don't know a priori what molecule will have these properties. Even in a tiny space of 10 millions, these tools can find the property, and this is the main solution and the main conclusion, in my opinion. Even the problem is very big, very big or very tiny.
Maybe you should include in your models the possibility that some molecules decay to another one and the space.
But maybe the genetic algorithm does something similar, giving to the target property, because similar Ellison can have very different properties. So they can, the mutations of the genetic algorithm can be something similar to this.
Hey, any more questions? No more questions for Rafael? Well, in that case, thank you very much again. And thank the speaker and thank all the speakers. Okay, and important for anyone, well, hopefully you'll all be coming to the afternoon session too, but we'll say it now just in case. So you probably know that the gala dinner is tonight. I think the dinner itself starts at 9 o'clock, but that's in La Chumbera. And so we'll all be setting off from Plaza Nueva We'll be setting off at about 8:30, but we ask you to try and be there by 8:15 to make sure that when we start going that way, you're all with us. Otherwise, you'll have to make your way there by yourselves in Magelos. So it's meet us in Plaza Nueva at 8:15 tonight, and we'll all go to La Chumbera. I don't think you need any tickets or anything, but maybe you should take your badges to make sure people can be recognized. Okay, so thank you very much, all of you, and see you this afternoon.